Okay, so polyatomic ion compounds. Let's first start by defining what a polyatomic ion is. And let's just bring that up. Oh, animations. I hate animations. Just write the first two bullets. They are a group of atoms that has a charge. Now again, my English isn't strong. You might think there's an error with with talking about atoms and then has. It's the group that we're talking about, and I'll draw a picture to explain what I mean in a moment. They are bonded together. Sorry. They're bonded to other ions by an ionic bond. So the ions can then also bond to other ions. They follow the same rules as ionic bonding, but with a group this time. And again, don't worry about that. That really doesn't tell us anything interesting. Now my next page here has the chart, and I don't. You know what? I am going to make you write this out. Yeah, I am going to make you write this out. Even though that chart is for you to use, and it is on the table, I am going to get you to write it out. So I'd like you to write this chart out for in your notes. Again, if you've got your ruler out and you're making an absolutely beautiful table, that's awesome. But if you don't, you make like 3 columns, it's fine. It doesn't have to be an actual table. That was just the convenient way in which to put it on the slide. And we are going to add one more to it. And you might have to memorize one, because it's not on the periodic table, but it is one that you will see, because I went through some of the homework problems that I assigned, and it is there. So I'm going to add one more on the bottom. I'm going to make you memorize that one. Yes, that's evil. When I teach you this next year, I don't include hydroxide and bicarbonate in this grouping. I teach it later on. The rest of them, though, I call the big 5. If you're memorizing, I have the students memorize the big 5: nitrate, chlorate, carbonate, sulfate, phosphate. And I like to order them in this way as well when you're memorizing. When you have to memorize them, you will in the future. Not for this course. And that's because I like to order them in increasing charge. You'll notice the charge increases as we go to the bottom. It has everything to do with what atoms are bonded to the oxygens. I'm hoping you notice that we have these certain atoms bonded to oxygen. It's oxygen that seems to be able to attach to these things, to these atoms, and make these polyatomic ions. turns out that oxygen has this kind of special ability to bond onto the side of other atoms. Again, I'm going way over the top of what, normally I would tell a grade 10 class, but you guys look fairly smart, so I figure I'd give you a little extra information. All right? With a regular grade 10 class, I'd say, here they are, now let's try naming with them. But let me just talk a little bit about what a polyatomic ion is and how it works a little bit. Again, not needed for this course, but it's good information. Let's take a look at chlorate here, all right? Now, let me show you how to build a chlorate. Again, you don't need to know this, but if we were to draw Lewis diagrams and think about what a chlorate is, it's made up of a chlorine, 1, 2, 3, 4, 5, 6, 7, all right? And it's made up of 3 oxygens bonded to it, 1, 2, 3, 4, 5, 6, okay? And this chlorine actually has to become a chloride first before I can build the molecule. So it actually becomes a chloride first. So we have a good old regular chloride. We looked at chloride the other day, right? You add you add an electron and you've turned it into an IDE ending, and that's the Lewis diagram for a chloride. Oxygen's kind of a tricky little atom. Oxygen is short 2 electrons from being happy. So oxygen can pull a little stick handling maneuver and can actually shift 1 electron around and make a pair out of those 2, which means it has an open area for 2 of them. What oxygen does then is it simply comes along and latches on and bonds on to one of these pairs on the chloride. And that can happen with 3 of them. That means the chloride, which now looks like that, also has oxygens, and I'm now going to use little X's to indicate the oxygens electrons. Little oxygens that have come along and kind of snuggled up against the chlorine, and you'll notice here, now the oxygen is surrounded by 8. So the oxygen is happy. Now I'm kind of jumping ahead a little bit because these are sharing electrons. We call this a molecule or a molecular interaction where they share electrons instead of trading. So this is actually a molecule, like water is a molecule, except it's a molecule that has a -1 charge. It's a molecule, because of the chlorine having 1 extra charge, this big thing has a negative charge, just like a chloride. That means I could bond it with something that has a positive charge. I could put that with an Na plus, and we'll make it a Lewis diagram too since we're at it. And I would have something called sodium chlorate. All right? So a polyatomic ion is actually a molecule that has non-metal atoms bonded together, but is also charged, which means it can stick together just like a simple sodium chloride. The only difference is the chloride now is carrying 3 extra oxygens around wherever it's, when it's bonded. Yes? Well, it doesn't really matter about where it comes from. Just like when we were drawing chlorine to chloride, right? Remember when we were doing this, right? And we just said it gains an electron to become a chloride. That's what happened, right? It gained an electron to become a chloride, and then in the chemical reaction, if there's oxygen around, the oxygen will latch onto that chloride and make it become a chlorate. Yep, okay?
How do you know oxygen can shift its electrons if we can't actually see it?
That's a good question. That's the same question. It's the same question as Megan. How do we know? We have a theory, and the theory works great. In other words, the idea of having electrons shift and making these interesting bonds, it works perfectly in explaining what we see. So we don't know. We think, and it works really well at this point. And we've not seen any evidence to contradict it, so we use it. All right? They're good questions. You guys want to know, how do you know? And they're ideas, and they work well. And so I'm presenting you with the idea, the theory that we believe is taking place. All right? So that's a wimpy answer, but it is. We don't know. It's an idea. Wilson?
Remember when you said something about, like, the lumens or something like that, and how they thought that there was 4 elements?
Yes.
And how because they never tested it and, like, tried to...
Yes.
They were really wrong?
Yes.
It's like the same thing.
It's similar, but we test it. We test it. We do test it. Oh, Wilson's going, tell me about it then. Tell me the proof. Oh my goodness, you guys, okay. Recording all this good stuff, so who's not here today? They're going to have to, Jaden's going to have to listen to all of this blah, blah, blah. Anyway, okay, you want to know how we think we know this. Again, this involves grade 12 ideas that I will be teaching you in grade 12, all right? It involves all of those funny-looking pictures on the back poster right there behind Abby, right? All those funny pictures of all these funny things. When we take that idea, which is called quantum theory, and we apply it to atoms, what the quantum theory does is it places the electrons that I've been telling you about here in certain specific spots around the atom. That's the theory. That's the idea, right? Okay? In grade 12, I teach you about the quantum theory, which kind of builds the atom, which looks different than this. This is a simplified version, okay? That theory then has another theory that blossoms off of it. Quantum theory has a second theory that we call VSEPR theory. It stands for valence shell electron pair repulsion theory, all right? Now that theory explains in 3-dimensional space where exactly the electron pairs sit, okay? We represent it as if it's flat on a board because it's really easy to start that way. But in reality, all of these things that I draw has a 3-dimensional structure to it, we believe. The theory is that, okay?
Wait, so the electron parting...
valence electron pair repulsion theory tells me the 3-dimensional shape of that chlorine. Okay, all right? And that 3-dimensional shape is actually what we call a tetrahedral shape. It is like a little tripod, all right? Where's my tetrahedron? You went down this path, man. I'm going to give you the whole thing. That's a tetrahedron, okay? I think of it like a tripod with a camera on the top, okay? And this model represents a carbon atom. And you guys will say, how do you know? And I'll just lose my mind. Anyway, this is a representation of a carbon atom. Now, it turns out that VSEPR theory and quantum theory predicts the shape of this carbon atom with hydrogens on it. Let's imagine these are oxygens instead. It wouldn't be a carbon atom if it was, but it doesn't matter. It predicts this shape to be a tetrahedron. In actual fact, that's exactly the same shape as this chloride ion. It follows the same set of rules. And with a chloride with only 3, it looks like that. Okay? So this chlorate polyatomic anion has a charge of -1 and has a shape of this, like a tripod without a camera on it. Okay. That's the theory. It turns out we can look at shapes of molecules in the laboratory. What physicists do is they can make a solid of, say, sodium chlorate. And it's a crystal. It's just like a salt crystal. Probably doesn't have the same shape as a salt crystal. It might be a different shaped crystal, but it's a crystal like a big chunk of piece of salt. You following me? Scientists can fire X-rays at that salt crystal. They can also fire neutrons at that salt crystal. It doesn't matter. One's called X-ray diffraction. The other one's called neutron diffraction. You fire it at the crystal, and the X-rays will bend depending on the distance between one nucleus and the other nucleus. So out the back end of the crystal comes this funny pattern of X-rays. All right? Comes out the back. If you don't believe me, I got a demonstration I can show you using visible light, but we're running out of time here. Anyway, maybe at the end I'll show you a diffraction pattern of a laser beam, but it's just like a diffraction pattern of an X-ray. All right. When we look at this pattern that comes out the back end of the crystal, and you do lots of mathematics and physics that scientists know by testing, they can find out exactly where the oxygen atoms are with respect to the chlorine in the middle. And when they work their way backwards using the math and the experiment, then they find the shape that we predict from the theory is exactly the same. Thank you. Thanks. Exactly the same as what we see from the experiment. That's why we know it. Because we do experiments and they turn out to be the same. Didn't I do this once already? No, but I mean in general, this whole idea is exactly what it was the other day. That's how we know it to be true.
Sounds good to me.
And that's why we, in our minds, we say, an easy way to explain it is oxygen does a little shift and sticks on the side, and then we can explain it. So we use it. Yes?
Why do all of them have 8 endings and then hydroxide has 5?
Well, this is essentially a carbonate with an H stuck on the front. So it's going to get the 8 ending. Hydroxide is really a completely different thing. It's a hydrogen and an oxygen as opposed to an element other than hydrogen and oxygen bonded with oxygen. So it's really a different version of the other ones. The other ones are very similar to each other, and hence they get the 8 endings. All right? Again, the origin of the ending 8, I couldn't tell you where the origin of the ending "ide" was the other day. Maybe something I could look up, but it's a different thing. Okay? There is one more I want you to put on the bottom. NH4. Oh, you want the name. That's the formula, by the way. NH4, it is +1. It has a charge of +1. And this is ammonium. This is the ammonium ion. So if you're adding to your group ammonium, NH4+, and it has a positive charge. So it's the only positive one I'm going to have you learn. So it actually behaves as if it's in group 1. Okay? And it looks like a tetrahedron, and I'm not going to tell you why. You already got that story. Because it actually has the 4, right? And ammonium looks like this, right there, with a charge. Boom, ammonium ion. Okay? All right. I got to be careful when telling you guys extra stuff. Just put examples, e.g., don't write so much. And write down aluminum chlorate. That's it. We don't need all this big boxes and things like that. That's the person who, and again, names to formula, formula to names. You can see what we're doing here. I'm going to do this a little elongated, but it's exactly the same as what we did the last day. Even though there are going to be 3 different atoms in our formula, in this case, aluminum, chlorine, and oxygen, it's still a binary compound. It's binary. Actually, many textbooks and teachers will say, oh, you can't say it's a binary compound. It's actually called a tertiary compound because it contains 3 elements. But if you think about the structure, there's always a positive chunk and a negative chunk. So you name it as if it's only got 2 pieces, even though one of the pieces has 2 elements in it. So it's still binary in nature. We have the aluminum chunk and we have the chlorate chunk. We treat it just like we did the last day. So aluminum, we write it down, Al. Again, the charge, I'm hoping we're getting good at it. It's in group 3. It's a metal, +3. Chlorate. You've got this chart in front of you. It's on your periodic table. Go to the chart, write it down. Put it in brackets, ClO3. Again, put the charge, but I'm hoping we get so good at this that we're not writing those charges down. We're thinking about crossing them over. So 1 crosses over to there. We don't write the 1. The 3 crosses over on the outside. That means we need 3 chlorates. And that's not a big deal. The brackets encompass the chlorate so that we can treat it as if it's like a chloride, right? So we put the brackets for that. So what's the overall formula? Al brackets ClO3 brackets 3. That's the way I say it. So if I was asking you to say it to me, you just simply say Al brackets ClO3 brackets 3. That means we need 3 chlorates to satisfy the aluminum. Now let's look at this a little critically though. How many oxygen atoms are there in this aluminum chlorate though? How many oxygen atoms would there be? What do you think? What do you think, Marissa? Yeah, 9. There are 3 groups of 3. There are 3 chlorates. Each chlorate has 3 oxygens, 3 times 3, right? So there are 9 oxygen atoms in there. I put quotes around the O so it doesn't look like a 0. Does that make sense to everybody? There are 3 chlorine atoms in that particular thing. And there are 3 chlorate polyatomic ions in that thing. Okay? Zinc bicarbonate. Let's see if we can do this in one shot without putting the numbers and crossing it over and da-da-da. Cross it over in your mind if you can. Now, zinc was that special guy. Zinc is a transition metal, so we need to track down the charge. I'm going to put it in this big box here. Oh, I got red going. I want yellow. Zn. And I'm not going to track the charge down yet. Bicarbonate. I'm checking in my chart here. HCO3. And I'm looking at the charge -1. I've got it in my mind. What's the charge on a zinc ion? Yep. +2. So where's my 2 going? Where are you going to put the 2? On the outside of the brackets on the carbonate. So the +2 came down here. This is 1. Done. Zinc bicarbonate. Okay? Pretty straightforward. I'm not getting a whole lot of emotional response from you guys. You seem to be pretty... Calcium hydroxide. We are naming these things. These are the new ones. They're made up of more than 1 atom. This is a chlorine with 3 oxygens. I had them add 1 more to it called ammonium. And it is NH4, and it has a +1 charge. So I haven't used one of those yet. Anyway, when we do the formula, we do it just like before, except we just treat this as if it's one thing. So calcium hydroxide will be calcium, and hydroxide is this guy, OH. I put brackets around it as if it's one thing. It has a charge of -1. I'm going to cross that over in a moment. Calcium has a charge of, what is it? Somebody said it back there. +2. So the 2 comes down here on the outside of the bracket. The 1 goes there. 2. That's calcium hydroxide. So it's just like the other stuff, except now we've kind of clumped a few of the important ones together like that. You get to use this table. It's actually on your periodic table. This one, I forgot to put on it. You're going to have to memorize the ammonium ion. All right? Actually, you know what I want to do? Let's, do that one. Do iron 2 bicarbonate. And then I'm going to stick one in with an ammonium in it because I don't have any examples with ammonium. So this one has obviously a multivalent metal. Remember, the 2 tells you what charge it is. You don't even need to go to the periodic table unless you need to find the symbol for iron. But it tells you what charge to use. I'm not going to write it down. I'm going to have you guys just tell me what the formula is. And if you want me to put brackets, just say brackets. Oh, Allison, what do you got? Yep. Oxidation state of, sorry, the valence. I sometimes say oxidation state instead of charge. It's just it's the same number. It just has a slightly different meaning. Again, when you get to grade 12, you'll learn why we call it oxidation state. But it has a charge of 1, charge of 2. Yep. Around this one? If I have a 2 that's going to, if I have a number 1 that crosses over, then technically you don't need the brackets. But if there's a 2 that crosses over, you must have the brackets. Because the brackets tells us that it's not just 2 of the oxygens, but it's 2 of the hydrogens and 2 of the carbons and 6 oxygens. So yeah, the brackets are important. Let me, yep.
I think know that it was plus 2 enough.
Because in the name, the brackets tell me what charge to use. It's right there in front of you. Okay? If I wanted it to be 3, I would have said iron 3. Okay? Let me clear the slide here, and I want to use this box to just do a couple more. I'm just going to make some up here as we go. Clear. Where's clear? Clear ink. Okay. And let's go with ammonium chloride. Now notice that says chloride, not chlorate. So chloride is what we were doing the other day. Right there, it's just a C, and it's got a charge as determined by whatever rules we use. Ammonium is one of these polyatomic ions I asked you to add, and again we do it the same way. So NH4. I'm always a fan of putting it in brackets because I might have to cross something over, but I might not need it. We'll see. Chloride, Cl. The ammonium has a charge of +1. What's the charge on the chloride? -1. 1, 1. That's done. Now in this case, because there's a 1 here, I didn't need the brackets. If you left it during a quiz or test, I'd say that's fine. But if you were reading a textbook, the textbook wouldn't have the brackets because it's really not proper, not needed. So you could rewrite this as NH4Cl. Okay? Did you see what I mean? Let me give you one more example with an ammonium. Too bad I can't erase it. Again, I got to clear the whole thing. Let's do clear. Let's do ammonium nitrate. Ammonium nitrate. That's actually a type of fertilizer. It can be used in explosives. It's an exciting molecule. Yeah, anyway. Yep. Okay.
All of our other ones, like the nitrate and everything, they're always at the end.
Yep.
And they only
It is, because it's got a plus charge. And if it's got a plus charge, it behaves as if it's a metal on the left. And therefore, it gets the metal position up front. That's how you determine where to put the ammonium, and it always goes first. Okay? It's a good question. So, ammonium, NH4. I'm hoping you're ahead of me, but maybe you're not. Again, I like to put brackets because I don't know whether I'm going to have to cross anything over. What's the nitrate? Formula for nitrate. Jocelyn, what do you got? NO3. What do we got for charges? Jocelyn, what do we got?
nitrate is -1.
So 1 and 1, right? That's it. That's the molecule. We can rewrite it NH4NO3. Now, some students sometimes say, well, let's put all the N's together. But you don't in this case. Because then it doesn't indicate to you that it's made up of an ammonium and the nitrate. So we don't put them together. So you might, if you get something like that, you might think, oh my goodness, what can the name of this thing possibly be? But because it's an ionic compound, it always is made up of two parts. Name the positive chunk, name the negative chunk. Hence, it's an ammonium and a nitrate. Okay? It's never ever like this. It's never nitrogen 4 nitrogen 3 oxide or something like that, where you just try to rattle off, you know, what it is. Like it pretend to make it up. That's never the correct answer. That's like me trying to speak French. It never works out nicely. It's really poor. It's not real French. Anyway, name the positive chunk, name the negative chunk. Okay, let's go on to some of the others. Let's now go back the other way. This is formulas to names. It's not a big deal. You can just put EG again. You know, we're just doing examples. It's not rocket science here. Even though you could use ammonium nitrate as a fuel for a rocket. But anyway, we won't get into that. Again, the name for ionic compounds always has two pieces. A positive name and a negative name. The positive name tends to be just the name of the ion, right? Positive ion, sodium ion, magnesium ion, potassium ion. The negative name changes to "ide" if it's just the element by itself. If it's a polyatomic ion, it could end in 8. It could be a hydroxide. That's a special case. So what is this called? Yeah, Marissa? Lithium carbonate. So lithium with a carbonate ion. A front and a back. A positive and a negative name. Lithium. Oops. Carbonate. I was thinking chlorate as I was writing. Concerns? Questions? As long as you don't ask me, how do we know? How do we know? You guys love that. How do you know? So you'll notice we got brackets, we've got 3s all over the place. We're not worried about that outside 3. Where did the outside 3 come from? Yep. It came from the crossover from aluminum. So I'm not worried about that. So I'm looking at what's in the brackets so I can name the thing that's in the brackets. So what is this stuff going to be called? Yep. Yeah, aluminum nitrate. Everybody staring at me as if to say, bring it on. I like it. Now I'm hoping some bells and whistles are going off at this point. Not that there's actual bells and whistles going off in your head, but anyway. What are we worried about right away when we see that metal? What are we thinking? We need to start thinking right away. As soon as we get these guys, we got to think something. Yep, Mackenzie? Goodness gracious. You want to commit to copper? Well, let's slow down. Let's slow down for a minute. That it's copper, and I've got to pick one of the two, right? So let's hold off on picking at this point. You see what I mean? So it's copper, so it's one of those ones that we've got to have two options. So I always go copper, and then I leave the brackets blank. I worry about that last. What's the last chunk of this thing called? Mackenzie, what's the back chunk of this thing called? What is that thing called?
It is carbonate.
Carbonate? So it's a carbonate. What's the charge on a carbonate? Yep. Charge on the carbonate. -2. So I've got to think, what value of copper crossover is going to get me this? Now you'll notice there's no brackets there. You could put them in if you want to help you think it through. Brackets, which means there's a number 1 there, right? So what value for copper did it have to be such that when you crossed it over, it resulted in a 1 beside the carbonate? What did it have to be? Got to think of your possibilities. What do you got, Megan? Yeah, it's a copper 2, because 2 and 2 would cancel away. That's what happened there. Okay? So that's a copper 2 carbonate. And that's where the brackets become tricky. Stick them in if they help you think it through. Okay? All right. Good work. One joke. We're busy. This is a good one. I like it. This is a measurement one. It's like science. How do you measure a snake? Maybe we should change it. What units do you measure a snake in? Anyway, in inches, because they don't have any feet. Yeah, it should be what unit do you measure a snake in, isn't it? Is that better? Yeah. All right. What do we have here? What's this stuff? Yeah, Mackenzie, what do you think? Gallium?
Gallium and phosphate?
Yep, it's gallium and phosphate. And how many charges does gallium have? We hardly ever use gallium. Take a look on your table. Does it have like more than one possible value for its charge? No, it can only be 3, so we don't need to worry about brackets or anything like that. So that's just gallium phosphate. Okay? All right? Okay. So now you'll notice at the bottom you can do section 2, part 1. In other words, you can do now the rest of the chart, the rest of the thing. But you know what? I want to do a little summary with you, and then I'm going to just let you work. All right? And then I'll come around. So let's do some examples where we are putting it all together. Sometimes we have to use 8, sometimes we have to use IDE. So we're going to do a couple of slides where we're just practicing the naming. So now we've got to keep a handful of things in mind. Number 1, is it nice and simple, right? And if it is, then the back name has an IDE ending, right? Or is it a complex one, where the back name, the negative name guy, has an 8 ending, or perhaps something else, depending on the table. We also have to be thinking, does it have more than one charge? Do we need to go and look for our charges? So we've also got to be aware of that stuff while we're naming, okay? Do I let you work quietly on A, B, C, and D, and then we come back and take it up together? I think maybe that's the plan. Or do you want to do it together? Together? We'll do it one at a time. Together. You got the first one done? We'll give... Oh, all right. Yep. Mm-hmm.
Well, other than the 1, we do 8, and then another one is 5.
Yep. Yep. That's exactly correct. This is bringing the two things together, right? And then our brains have to think of two things separately. It's, if I were to give gum out at this point, as you do all of this, you'd be falling on the floor because you wouldn't be able to regulate yourself. It'd be chewing gum and IDEs and 8s and, no? Use your pencil. Don't use pen as you're trying these. Because when you make a mistake, it looks like this. You got the name?
No.
Oh, you're going to ask a question? Yeah, I know. What do you got? Well, there's a whole family of them that I haven't taught you. That can be named through all of it. There's, not only is there a chlorate, but there's a bromate, and there's an iodate, and there's an astenate. And not only is there a sulfate, but there's a selenate, and there's a tellurate. It's fun. And not only is there a phosphate, but there's an arsenate and an antimonate. And you will learn about those next year, because I will make you learn all of those. They're exciting.
But are there any that aren't halogens, or can you just...
You mean non-metals? You mean non-metals?
Yeah.
Yeah. Manganese has the odd ability to behave very similar to a nonmetal. So we actually have some polyatomic ions that have manganese in them. We have permanganate, and we have manganate. And so there are the odd atoms in the transition metals. Manganese is the big one. Really, I think tungsten can do it too, and molybdenum. Again, they're in the same group, so they have the ability to be similar. Actually, no, it's chromium. No, tungsten can do it. Chromium can do it. I don't know about these two guys, but there's the odd one that can. There's the odd one. Yeah. Okay, we've babbled on. What's the name of this one? Yeah, Mackenzie, what do you got? Fluoride. Very straightforward. A zinc with a fluoride. Zinc fluoride. Next. Yep, Justin?
Aluminum nitrate.
Yeah, excellent. Aluminum nitrate. Yeah, Sammy? Yep, very good. Sodium sulfate. And last. Yeah, Megan, what do you got? Yeah, very good. Barium phosphide, because it's just the P by itself. It makes it an ide. We didn't have any of our polyatomic ions, or sorry, we didn't have any of our metals with more than one charge in there, but that's okay. And let's do a few of them going back the other way. And then I will give you all kinds of practice, and then you practice away. So again, when we have a quiz or a test, I supply you with a nice table that looks like this. It's got that nice chart with the polyatomic ions on it. I failed to remember to put on an ammonium, which means you have to memorize that one. Gotta memorize something. If you know how to use your periodic table to find the charges are all there. So really, this is an exercise in knowing how to use your table. Okay? A little bit of a tricky one here, maybe not so bad. Somebody have a formula for that first one? Yeah, Mackenzie, what do you got?
I'm not sure if this is right, but AG2 bracket PO4 bracket.
AG, and then bracket PO4, you want to close it up. And you want to put the 2 here because it came across from here?
Yeah.
Take a look at the charge on that phosphate again. It's a tiny one. It's a 3. There's a little 3 up there. See the 3?
Yeah.
That's the charge we need to cross over. Other than that, right, the logic was correct. But phosphate is a 3 charge. Okay? Very good. Didn't need the brackets. So, but if you have them, let's say you're getting into the groove of writing the brackets, and then you realize, oh, I don't need to put anything there. You don't have to erase. On a quiz, I'm not that picky. In a textbook, they won't have it. So you just would have to be aware that it's not there. In your mind, you can put it there, right? How about this one? B. Yep, Marissa, what do you got? ClO3 bracket 2. So we got 1, and the calcium's 2, and we got to cross it over. I like it. Do you understand why it's like that? Get the hang of it. Calcium is +2 like it was the other day. On our table, we know the table will tell us that this is 1, and the 1 will go over there, just like it did. Potassium nitride. Yeah, Megan? Sorry? Yes. Yep. That's correct. I thought it was a nitrate. In my mind, I had nitrate going on. I'm like, what is she doing? Oh, no, that's correct. No, that's good. It's a nitride, so it's just nitrogen. We got to cross over the charge of 3. That is exactly correct. That's me all messed up. Magnesium hydroxide. Magnesium hydroxide. Allison.
MG bracket OH bracket.
Yes, excellent. Very good. Some students get mixed up. Sometimes they think, look, there's no numbers with the O and the H, so I don't need the bracket, right? Some people think, oh, there's a number there, I better put the number. But you do need the bracket. You must. It's not just 2 H's, it's 2 OH's, all right? And that's very important. Move on here, and you can see there some textbook questions, and then the rest of the sheet. You can just do the rest of that sheet. And this is the type of stuff that the more you do, the faster you get and the better you get. Like I said, it's just like learning a language. So, and I'm not necessarily saying you need to master that language. Well, you do need to master it. Of course you do. You got to. But like when you get to grade 11, I always tell them, if you can't, if you are hunting and pecking for things on the periodic table to get a name, and we're to the point in the course where I need you to find the name like that because I need you to find other masses and things. In other words, that's just a little tiny part of the question. You need to be able to find them. You need to be able to do the name quickly and functionally. All right? Okay, so at this point you can work. I'm going to stop the recording, but I'll bring up that sheet for those of you who didn't print it out. Where's my recorder?